So we'll put it here all by itself so that we can look at it and gaze upon it in all of its glory. So we're first of all going to need to know what these curves look like. So let's go ahead and sketch them. Whoa, that's interesting. Looks like a crayon. Here we go. So cosine, the cosine of x looks like this. And this, there it is, it's symmetric. Here's negative pi over 2, here's positive pi over 2. And so apparently this is the region that we're interested in. So let's set this up, the mass. So you have the three things that you need to do. First of all, set up the mass, negative pi over 2 to pi over 2. Then that's the x values, by the way. Sorry, I put my podium down there because Excel. There, this is better. There we go. Now I don't have to hunch. Okay, so we've got this. And then the y values goes from 0 to cosine of x, and the density is y dy dx. So far, so good? So that's the setup. That's the most important bit. So if you do nothing else on this quiz, get that in there and you'll be in good shape. So the mass. So then we have to evaluate this. Hopefully the one on the quiz won't be as difficult as this. This one isn't bad though. So this will be y squared over 2 evaluated from 0 to cosine. So I'm just going to cut to this cosine squared of x over 2. So this is after doing y squared over 2 and plugging in. Hopefully that's not the problem that you're having. It's this next step. So now you just need to either look up or remember the antiderivative of cosine squared. And so I will just remember it. But if you don't know it, if you need it, it will be on the exam next week. So it probably will be needed somewhere. So I'll make sure that this particular antiderivative is there. So this is going to be, let's see, theta, not theta, it's x. So we have x over 2 plus sine. I'm still thinking of double angle formula. Sine of 2x over 4. So that's the antiderivative of cosine squared. And then you just have to plug in the limits. X equals negative pi over 2 to pi over 2. So this will be 1/2 times, I'll do this carefully. So pi over 2 is pi over 4, plus the sine of pi over 4 minus negative pi over 4, because I'm plugging in negative pi over 2, plus the sine of negative pi all over 4. Sorry, that should be, oh yeah, that should be a 4. That should be a 4. Okay, there's lots of brackets and parentheses there, but the long and the short of it is that this is 1/2 times pi over 4 plus pi over 4, which is pi over 4. Yeah, because the sine of pi is 0, sine of negative pi is 0, so all that's left is pi over 4s. Did I do it right? Did I get it? Hopefully. I guess it's not back of the book, so you don't know. So there's the mass. So, whoa, I'll get that in a minute. Where you can reach really far with it. You can do it. Yeah, good job. Okay, so that's the mass. The second thing you need to know is the center of mass. So x bar and y bar. And these are the moment about the y-axis over the mass and the moment about the x-axis over the mass. But the more important thing is that you do this. You do a double integral. Here, I'll put the pi over 4 down here. So whatever the mass is, that should go down there. But the double integral will be a double integral of, of x times the density. So dy dx. So you're going to throw an extra x in there when you're doing the average x value, throw an extra y in there when you do a y value, average y value. The rest of this is the same. What is this? 0 to cosine of x and negative pi over 2 to pi over 2. So that shouldn't be terrible. Well, okay, I see. There is a terribleness, isn't there? The next one isn't so bad. Oh, it's terrible as well. Yeah, they're terrible. Okay, I admit these are terrible. It's the outer integral that's so terrible. So here, let's just get to the outer integral. So the two outer integrals that you're going to have to deal with, negative pi over 2 to pi over 2 of x times cosine squared of x over 2, which I'll just put the 1/2 over there. So this one is from the x bar. So this will be 4 over pi times this. So if you do the inner integral, the only thing different between this and what's up here is the x. And so the x is the thing that's going to be annoying. So I would use integration by parts at that point. And then the y bar, that one will be sort of similar, but it is also pretty ugly. It's not 1/2 anymore. So in this case, because what you do is you put an extra y in there, you have this y squared. So y squared ends up being y cubed over 3. So this will be 1/3. The integral from 1 over, there it is, to pi over 2. And then this will be cosine cubed of x dx. Okay, so let's do this without doing it. In other words, I'll just tell you what you would do. So the first one, this one isn't bad. I mean, it is bad, but it's not as bad as this one. This one, what I would do is I would use integration by parts. Let u equal x, du or dv is equal to cosine squared. That will give me the two components. It'll work out relatively nicely after the first just one integration by parts. So that one's not terrible, but I mean, I can get the answer. You could get the answer yourself by going on Desmos or whatever your preferred computer algebra system is. This one is a little bit uglier. The way that I would do this one is I would use u substitution. You might say, well, what are you going to use u substitution for? Well, I'm going to do this, and you're going to lose your mind at this point. The u is going to be sine of x. And it's like, where does the sine of x come from? Well, I'm using a couple of identities. I'm going to take that cosine times cosine squared of x. So here's how this looks. I probably should have noticed that this was going to be ugly and not assigned it. But anyway, then this is cosine of x times 1 minus sine squared of x. And if you let u equal sine of x, then du is equal to cosine of x dx. And you can kind of see here that the cosine of x dx, there's my du, the u sine. And so, like I said, it is ugly. So if you got to this point, you should be super happy with yourself. And I am happy with you as well. Same thing with this one. If you got to this point, way to go. Here's my really bad thumbs up emoji. It looks really grotesque, doesn't it? Almost looks like a pinky, doesn't it? Okay, well anyway. So yeah, let's not spend our time doing this. We got the setup. You understand? I get it. You did. I chose poorly. So my bad there. But you know how to do these. Is there anything else? So the main thing. So here's what I want to make sure we focus on. Okay, is mass. What's the mass? The mass is double integral over whatever region, and you throw the density in there. So that's the mass. And then when you're doing x bar, you do the same thing, but you throw in an extra x. So you see the extra x there. And for y bar, you throw in an extra y. So that's the important difference between those three. Also divide by the mass, whatever the mass is. Okay. So as far as, yes, sir.
When we look at the graph, because it's symmetrical, can we just assume that the x bar is 0?
Oh, good point. Yes, in this case you can, because the density is also symmetric. So it's symmetric. Good point. Very nice. Yeah, I love that. So yeah, this graph looks like this. The only reason I would say no is if so here, the density also is symmetric about the y-axis. So in other words, the density right here is the same as the density right there. So since the density, here, that point has the same density as this, because the density is y. If the density had an x in it, I'd say sorry. Unless, like if the density was like this, then it would also be symmetric. So yeah, so that's a clever way of doing it. Yes, x bar is 0. Very nice. Wait, is there another reason? Can we conclude this? Just a minute. Get that thumb out of the way. Ooh, this, yes, this is an odd function. How do I know it's odd? Well, cosine is squared. Cosine's an even function, but when you square it, for sure it's even. And you multiply it by x to the first, so you have odd times even, which is odd. And then, so that's an odd function, meaning that it's Maclaurin series, which some of you don't know what a Maclaurin series is, but don't worry about it. Maclaurin series has only odd powers in it, and it's symmetric about the origin, which means that whatever you get here will be exactly the same as what you get. Oh wait, odd. Can I exploit the oddness? Well, it must be 0, because you said it's symmetric. Yeah, it's got to be 0. Odd. Sorry. Yeah, they cancel each other out. Yeah, the areas cancel each other out. Yeah. So whenever you have odd, I just canceled out the whole thing. But okay, let's move on though. Is there anything else? Those are the main things. Is these 3 formulas that I'm really hoping that you got. Okay, I've got one that I want to do, but it's not one that you were assigned. Where is it? It's here somewhere. Oh, there it is. Yeah, this one. We're going to do this one as well. Maybe not right now, but maybe a little bit later. Yeah, let's do the quiz and then see how that goes. So here's what I'd like you to do with the quiz, is start by writing down the formulas, like in terms of this problem. So start with that, and then if you get the formulas, then you compute. So that way you don't have any blanks. At least you have the formulas. Start with the mass, and then go from there. Hopefully this isn't as bad as that cosine. There's no cosine on here, by the way. It's just nice polynomials. And there will be one place where you have to square a binomial. I know, it's going to be terrible, but you can use FOIL. If you get to that point, it'll be when you do the moment about the y, the average y value, moment about the x-axis. I can do the picture for you. There's an extra one. Let me have one more.
You have 2 extra over here.
You have 2 extra? Why do I have so many extra? Oh, it's these 2 are missing. I understand. Yeah, I should have known. I printed fewer. Okay. All right, I'll get this up on the screen for absent people. Let's see. Calculus. hoping that you can view the actual integral, but if you can't, at the very least, write down your formula, so you've got whatever, it's the mass, you've got some sort of double integral, tell me what it is, your limits and so forth. Same thing goes with the x bar and y bar. This shouldn't take too long, other than the squaring of the binomial in the third one. Can't imagine it should take you too much longer. I guess I can come gather homework since I haven't done that. While you're finishing.
Yeah. No, that was wrong. Look at the second. My why. None of it's not
I guess that would be, having that sort of self-knowledge it's worth something. I always appreciate it when people quit their own test. You know what I'm saying? You think? You know? We're finishing now. I don't want to rush you, but you're almost done. It's been great. Good job. Pretty good. No calculator today. We have some over there. You don't have to do it.
I couldn't find it in my bag.
Oh,
It's
no.
buried in there somewhere. And I was just like, okay, well, I got down fractions.
Yeah.
I'm really it's not accurate form, so I didn't calculate out decimals, so
Yeah.
I'm thinking I should get extra points for it.
Yeah, this is fine, but I do if you in future. If you need one, it's out of the drawer here.
I think I'm right, honestly.
I got one million, so I think I was on
Okay. All right. Well, if you aren't quite done, at least you have your double integrals. So we can try to wrap things up. Oh, I know. You just like to meditate. It's like yeah. You got a thing box there. Oh, you got the double integral. You got the double integral box there.
Right.
And let's see. There's also like to take the right down. Oh, come on! But you know you did it wrong. Okay. But yeah, so just put say, oh, here's what you finish this at. So you just box the double integral. I'll give you credit for the double integral. You got the double integral? You got it. Yeah, the double integral. Good job. Do you have the double integral? For the second one? The last set? Where is y bar? That place here? Oh, did you x bar here? Okay, so you've got numbers. And you're all set. Good job. Oh, Y bar. Oh, you're just switching it. Okay, but it's here. Good. And then you got yours? You got something? You got something? You got something? This is your Y bar. You got an answer. What are you doing? You got answers. Don't steal that. Good job. See who else got to rip it out of their hands. Oh, yeah, you're like me. Here you go. Let's see, do you have a double integral? You got a double integral. That's the start. You got double integral. Oh, you're just holding on to it. Oh, you guys have answers. Okay, do I have all of them? Oh, Daniel's holding out on me. You have a double integral? Oh, you're done. Oh, you're just meditating, I see. Now I've got them all. All right, let's do this. Okay. So I don't know. I guess we're going to find out next week, because next week when we have this on the exam, any double integral, I'm going to give you the answer. So you're going to be like, well, you have to show your work though, basically. So I don't know if it would have helped you if I had told you the answer to this ahead of time. Then you'd have a target to shoot for. But we'll find out next week. This is a quiz, so it's not as big of a deal. But anyway, here's my answers. So the first thing, this is what I'm really interested in. Do you know how to say that the double integral of the density over this region is that's the mass? So that's the first thing. You got half credit for that. And then if you get the right answer, that's great. So it's 8/3 was the final answer. So good. I'm glad that you got it right. Yeah, so it's a pretty straightforward. It's a nice polynomial. I tried to pick easy things. I guess maybe you got scared when you got down here. So 8/3, I did 1 over the mass. So that's 1 over 8/3, 1 over the mass. So 3/8. But other than that, here's my double integral. I threw an extra x in there. So you see the extra x. So that got put in there. And then the rest of this one was pretty straightforward as well. There was no squaring of binomials. I got down here a little bit more work, and I got 1 as my x value. And then the y value, this is the one that was a little bit more grueling, because you have to do the integral of this with respect to y, which gives you y squared. And the y squared, when you plug this in, is painful. But hopefully it didn't cause you too much pain. So look, I did it in one step here. I did y squared over 2. That's what this 2 is. And here's y squared. I plugged in and did the squaring of the binomial. And then there's some work and some more work and some more work. And then finally you get 1 out of that. So it was 1 and 1. So I thought that was kind of neat that it's 1 and 1. By the way, someone said, oh, I knew I got it wrong because my point was outside the region. And that's true for convex regions. The center of mass is always going to be inside a convex region. But if you have a concavity, like if you have a shape like this, you could have a center of mass right there, sort of outside the region, like a boomerang or whatever this shape would be. So just kind of an interesting thought. But let's move on. Today we're going to take a look at moments of inertia. Oh, I had Googled. Give me a sec. I'm going to Google this again. Just a sec. So I thought it would be fun. Let's see, images. Yes, here we go. So here, I don't Google, I DuckDuckGo. But so I DuckDuckGo moments of inertia, and here's what came up. And so it's so exciting to me that we have an engineering program now, because back in the old days, no one cared about moments of inertia. Like, they're like, why do we even care? Well, you know why you care. It's because of pictures like this. You've got something spinning, and you want to compute the amount of energy, kinetic energy, that's stored in this spinning object. And so, like a flywheel or what have you. And so you have to use the moment of inertia to figure out that thing. And these formulas are given to you. So, for example, the disk, or no, this is, the cylinder, disk. If you have a flywheel, there's a simple formula for that. But where did that simple formula come from? Well, it came from calculus, of course. So that's what we're going to learn about today. It's simple, though. It's not as complicated. If you can do center of mass, you can do moment of inertia easily. So we'll do the moment of inertia. We'll come back to this picture because we're going to compute this, the one for the disc, well, the cylinder, they call it cylinder. So we'll do that one. We could do the ball, but we're not going to. But we could. So here's our thing. So we'll come back to that picture in a minute. So we've already done center of mass. Just to remind you, here's the, whoops, there it goes. Here it is, and there it goes. So there's the mass. We have center of mass. Here they are. And so we're used to this already. We've done these. Moments of inertia are just the next level. So notice that here, to get the moment about the x-axis, whoops, why is this not showing up? There it is. So to get the moment about the x-axis, you put a y in there. And the reason is that we're interested in the distance from the x-axis. And y is the measure of distance from the x-axis. The moment about the y-axis, you put an x in there. I point this out because it didn't matter so much that you knew that when you were doing this, because you could easily sort this out. The average x value has an extra x in it. The average y value has an extra y in it. But the moments of inertia are going to be similar, but they won't be as obvious. So let's go to the moments of inertia, because that's what we want to do today. Oh, first I should explain what is a moment of inertia. It's the resistance, or I think that's the right word, to motion around an axis of some sort. So here I will draw an object. Let's take something simple like a flywheel. So a nice circular. So this we'll do in just a bit. So we have this object. You can imagine, why did I do that? You can imagine that it is solid, like a disc, like a flywheel, solid metal disc. And we want to rotate that thing. So the moment about the moment of inertia about the y-axis is going to be the resistance to this sort of spinning motion. So you can imagine you're going to say to me, well, why would you ever put the axis right there? Well, I've seen things like this, especially when you deal with, valves, or turning on and off like airflow or whatever. You might have something like this that is a disc that is rotated through this axis. So you can rotate it this way, air flows, rotate it this way, it stops flowing. So that's what the moment about the y-axis is. And to compute the moment, what you're going to do is you're going to take the distance from the y-axis and square it. So you probably, those of you who know how to do moments for point masses, you take the distance from the axis, square it, and then multiply by the mass or something like that, or density. I forget the exact formula, but whatever. That's the way it's going to be. Is we're going to take the distance. So if you think of a little point here, that distance is an x value. So the moment about the y-axis, it will involve x values. The moment about the x-axis is going to it's going to be sort of this resistance to motion or momentum around, spinning around the x-axis like this. So I know what you're really interested in, though, is what if we spin around the origin? Because that's what would make most sense if this was a flywheel. So to spin around the origin, so this is the moment of inertia around the x-axis. The spinning motion around the origin, we're going to call that I sub 0. And it turns out that that is just the sum of these two moments. And there's a mathematical reason for that. But I mean, the easiest way to see it is that if you think of so that point has an x value and a y value. So here we're going to be doing something with an x squared, whatever. Here we're going to do something with a y squared. We'll have to throw density in here as well. But this we're interested in the distance from the origin. And notice that the distance from the origin is the square root of x squared plus y squared. But if you square that, you just get x squared plus y squared, x squared plus y squared. So if you just add together those two moments of inertia, you end up with the moment of inertia around the origin. So we'll do all three of these, but it's the third one that is listed on these. So those, that third one, the moment around the origin, generally, well, although those are three-dimensional objects, we're still dealing with laminas here. So I guess a three-dimensional object you could, yeah, but I'll be doing this to check those formulas. Okay, so here are the formulas here in all of their glory. So these second moments, the moments of inertia, you label them I sub x and I sub y. And on your homework, I just have, I think, I think there's just 3 problems. And I need to set one of them up. That's why I said we're going to be doing a problem. Hopefully we'll have time for that. So one of them refers to a problem you haven't done yet. I thought it would be helpful if I did it for you, if we have time. Okay, so let's actually do this for, oh yeah, this is related to kinetic energy. So if something is spinning, how much energy is stored? Here's the formula for kinetic energy, where you don't have to, we're not going to be using this, but it's just for the physicists. Like, oh yeah. So yeah, 1/2 mv squared is related to this, but this is 1/2 times inertia times this is the angular speed, angular rotational speed. So something's spinning, it'll retain some kinetic energy through its spin. So let's go ahead and do an example. Let's see, is this going to be painful? Probably, but I'll do it anyway. So this is related to one that we did, I think, on Wednesday. So give me a sec. I definitely don't have enough room. Oh, kinetic energy. Why does it say kinetic energy? Just a minute. Well, that's all right. I'm really most interested in doing the moments of inertia. So if we have time, well, we don't have time, to be honest, because I need to do that one problem that I promised I'd do. So let's just get this set up for the moments of inertia. So you have the inertia around, so ignore this whole thing, rotating, whatever. Yeah, I mean, we could rotate if you want at some point, but not right now. So you can go spin things. But right now, I just want to know the moment of inertia around the y-axis, which is going to be the double integral. Let's see, I need to draw this. Give me a sec. Hopefully this doesn't surprise you. We've had this picture before. 3, -3, and this is y is 9 minus x squared. Okay, so x goes from -3 to 3, y goes from 0 to 9 minus x squared. We have the kx squared dy dx, but the important thing is that the moment about the y-axis, you throw an extra x squared in there. So that x squared is the extra stuff. So it's just like when you're computing the average x value, you throw an extra x. For the moment, you're going to do an extra x squared, the moment of inertia. So let's go ahead. We can compute this. This is not terrible. The next one is more terrible, which maybe I should do or maybe I shouldn't. But let's crank through this. This one's not bad. So you have kx to the 4th y, evaluated from y equals 0 to 9 minus x squared. So this really isn't hard. So this is -3 to 3 of k times 9x to the 4th minus x to the 6th. Nice even function. Does that mean that I have 0? Can't be 0, could it? Let's see. So from -3 to 3 of, oh, sorry. I'm going to do the antiderivative now. So let's crank this out. It's k times 9/5 x to the 5th minus x to the 7th over 7. And this ranges from -3 to 3. So that, almost done. Did I do it wrong? No? What?
That k looks like a 12, and that 12 looks like a k.
Did that look better? Yeah, sorry, I was writing quickly because I'm thinking I need to do more than this. Okay, 3 to the 5th is 243 times 9. Oh, is that 3,000? What is 243 times 9? See, look at this. Even I rely on a calculator every now and then. So don't be ashamed if you have to use your calculator. So 9 times 243. It's 9 times 243. I should know this, but 2187. Wow, I was so far off. Not 3,000. Okay, so this is 2187 over 5 minus the same thing over 7, because 3 to the 7th is the same as 9 times 3 to the 5th. And then we're going to subtract off 2187 over 5 plus 2187 over 7. Is that all right? Yeah, we can do this. You know what? Maybe I'll just use the computer for the moment about the y-axis. So this is going to be k times 748 over 35. There, is that right? I hope so. I'll just fire up the computer here. We'll just crank this out for the, so give me a sec, and we'll just do this. You'll see how joyful it is. You use your own program, whatever it is you like. You know, I'll get mine. Here's mine. Let's put it over here so you can see it if you're curious what I'm doing here. I'll make it nice and big there. It's beautiful. So I'm doing the double integral. I'm just going to double check my math here. Of it was k times, what was the original double integral? X to the fourth times y. Okay, very nice. Where y goes from 0 to 9 minus x squared. Kind of embarrassing that I'm not using Python. X goes from -3 to 3. So, oh, I got it wrong. It was 17,496 apparently. So, but I could be forgiven because I was trying to do all of that math in my head. 17,496 over 35 times k. So I'm just copying this down. Now the double integral, so the only difference between the moment about the x-axis and the moment about the y-axis is the y-axis has an extra x squared thrown in here. The x-axis, you're going to put an extra y squared in there. So that's going to be my moment. Hold on a minute. Oh, why do I have a y there? Yeah, I have an extra y. I think I was right to begin with. X squared. I think I typed wrong. X squared times x squared. Let's get rid of this y. Oh, 8748. That's what I had. Okay. Okay, so we've got 8748. All right, now let's go for the moment about the y-axis. No, that's the moment of the y. Moment about the x-axis. Second moment. There it is. So saving us some trouble. The big trouble here is you're going to have to square a binomial, or no, cube a binomial. So I'll just write this down here. I sub x, and then I'll show you what I've got. This is k times 23,328 over 35 times, there it is. Okay, so here's, I just was too lazy to have to do all that. So then the moment about the origin is going to be the sum of those. So if we add those together, you'll get the moment about the origin. Okay, so I think it's time to take a look at that disk because this one was nasty. I mean, this whole business about, yeah, I don't like this one at all now. So let's do a disk. So what we have here is we have this disk, okay, whatever. It has a radius of r, and the mass is m. Okay, so the problem here is that to do this, so you're going to have to bear with me for a second, I need to know the density. So the density is going to be, let's see, density is mass per unit area. So we're doing laminar density here. So mass per unit area is going to be mass over pi r squared. So that's going to be the density. So I want to know the moment about the origin. And to do that, I'm going to first find the moment about the y-axis, the moment of inertia. And to do that, I do a double integral, this constant. So I'm just going to write that down as rho. So this double integral And you know what? This is a circle, isn't it? So can't we just convert this to polar coordinates? Yeah, let's convert this to polar coordinates. So little r goes from 0 to big R. We have 0 to 2 pi. And you have rho times x. And x is r cosine of theta. dr d theta. So here, this is x. So give me a minute here. So 2 pi, I should do x squared. Oh, now I'm discouraged, because this is going to take forever again. I looked at those formulas. I thought for sure they'd be easy and quick. And then once you throw the square in there, it's going to take too long. Yeah, it's going to take too long. So yeah, I guess I'll do this. This will be my job for Monday, is to do this, because I want to actually verify that the moment is the moment that's printed in your physics book. So let's go and look at the homework. So one of the things that I have you do on your homework, where is it? Give me a sec here. There it is. So the homework, here, I'll go find the homework here. I'll tell you right now, but you can look it online. It's these three, 17, 18, and 19. So you're supposed to find the moments of inertia for exercise 3, exercise 6, and then exercise 15. So 3 is pretty straightforward. I think you did that already. I don't know if you did 6 or not, but that's pretty straightforward as well. It's 15 that's not so straightforward, and that's this one, because it doesn't give you any numbers. And I know that when you don't have numbers, you start losing your minds. So I thought that I would get you through exercise 15. So where is my exercise? There it is. So exercise 15 describes this thing, and then hopefully you'll be able to set up the rest of this. So if I can do, oh, you can't see the whole thing because anyway, so here's exercise 15. Find the mass and center of mass of this lamina. It's an isosceles triangle. It has the legs here go out to A, and this is a right triangle, and it says that the density is proportional to the square of the distance from the origin. So that's the part that I thought would be the most difficult, and so I wrote that down there, proportional to the square of the distance from the origin. So if you think of a point here, that point is the point xy. The distance from the origin is the square root of x squared plus y squared. And if you square that distance, you get this. So anyway, once you have that, you can pretty easily set up a double integral for the mass. And that was the part that I thought would make you lose your minds, is trying to set this up. Once you've set that up, you can set up the inertia, the moments of inertia. For example, check this out. So you're going to need to do this, but for the moments of inertia. You don't have to do the mass. You just have to do the moments of inertia for this one. And so to do, here, let's just set this up. To do the moment about the y-axis, you throw an extra x in there, x squared. If I was doing the moment about the x-axis, I would throw an extra y squared in there. And as you can imagine, that's going to cause a little bit of trouble with that upper limit, but persevere. And then if you want to do the moment about the origin, then you're just going to do those other two and add them together. And you'll get the moment about the origin. So really, these moments, they're just double integrals. So I apologize for that disk. I thought it would be easy. And then once I saw that I was going to have to square the cosine, I will write it up for Monday, though, just to prove that I do get exactly what you have in all of these pictures here for a disk. That's where they got their formulas, is some mathematician sat down and did a double integral for them. So aren't you happy about the mathematicians who are willing to do that? All right, that's enough. I'll stop the recording in case you need to come whisper something to me. Otherwise, hope you have a good weekend. Stop it.